Module 1, Lesson 6, Newton's Method and Newton-Raphson Method. For this module, we'll then cover open method techniques like the Newton's method, derive its iterative formula, and apply that on a given sample problem. We'll likewise include the other version of your Newton's method, which is called the Newton-Raphson method, determine its convergence test, and apply that again on your sample problem. Open methods are simply techniques that are no longer restricted by the bracketing condition in selecting the initial values for their iterative process. However, since these techniques are no longer bounded by the bracketing condition, then as a result, some of these techniques eventually diverge. These methods, even though diverges, are applicable for both polynomial and transcendental functions. The Newton's method. This method is also based on a linear approximation of a function, much like the second method. The line that best approximates the graph of your function at the point on its graph is the line tangent to the graph at your given point. The Newton's method makes use of this tangent line based from an initial value x0 instead of a second line in order to approximate the root of your function. This method, again, much like your previous techniques, are applicable to both polynomial and transcendental functions. The Newton's method starts by setting an initial value x0 or xn selected without any conditions, like the other open method techniques, and then substitute it to your given function, deriving your value fx0. A line tangent to the function fx0 is then used to estimate a new root value, which is often referred to as x1 or xn plus 1. This is the graphical depiction on how the technique works. You set up an initial value x0 and determine the function fx0, and then obtain a line that is tangent to that given function. This tangent line will eventually intersect with your x-axis, thus giving you a new root estimate x1. Thus, in order to derive the iterative formula for your x1, we then make use of that tangent condition. Note that the slope on your line is determined based from the height of this respective right triangle and the length of this respective right triangle. With that in mind, we simply evaluate then your slope, which eventually the iterative formula is derived into this concept, where your slope is defined to be fx0 over x1, x0 minus x1, which is likewise also equivalent to the first derivative of your function at x0. Hence, we can now manipulate and solve for x0 by simply transposing x0 minus x1 to the other side, which is now equal to your function fx0 divided by the first derivative at x0, thus giving you an iterative formula for x1 to be equivalent to x0 minus your given function fx0 divided by the first derivative of your function at x0. The process is then repeated by substituting the computed value of x1 to your x0 or to your previous value xn, and then computing for a new root estimate x1 or xn plus 1. This process is then repeated until the terminating condition is satisfied, which is usually based from either an approximate error criteria, which is absolute error, or a relative error precision type criteria. Note that the Newton's method does not have that bracketing property, much like your second method, seen on your bracketing techniques like bisection method. Again, as a consequence, this method does not always converge, or some initial values for this given particular technique gives you a divergent solution. However, when it does converge, it generally does so much faster than any of your bracketing techniques. Let's try to evaluate then this given example. Let's solve this function using Newton's method with a terminating condition of EA less than or equal to 0.00001. We then begin by setting your respective function to 0 and then evaluating its first derivative, which we will then use for your iterative formula. We then set up our initial value x0, which is assumed to be any integer number. In this case, the value 4. Hence, on the first iteration, you'd end up with this solution, setting up an initial value x0, 4, substituting that to your function f(x0), which gives us the solution with a value of -6, and substituting 4 to your first derivative, which eventually should have the solution ending up with a value of 17. Substituting now these important values to your iterative formula gives us a solution for x1 with a value of 4.3529. We then apply our substitution process, setting your calculated value x1 as your previous value x0. And then the second iteration sets up now your x0 to be 4.3529. Substituting that to your function gives us this solution of f(x0) with a value of 1.0396. Substituting x0 to your first derivative gives us this solution that gives us a value of 23.02. Hence, we can now recompute for x1 to have this solution with a final value of 4.3077. We check if we could terminate the process by obtaining its absolute error, ending up with a value of 0.0452, showing us that we need to continue on the iteration. Therefore, we substitute your calculated x1 4.3077 as x0 for your next iteration. Hence, on the third iteration, your x0 now is 4.3077. Substituting that to your function gives us this solution with a value of 0.0175. Substituting x0 to your first derivative gives us this solution, which gives you a value of 22.2072. We then use these values to solve for x1, giving us an x1 solution equal to with a value of 4.3069. We then check whether we could terminate the process by obtaining the absolute error, which now turns out to be 0.0008. Thus, showing us that we need to repeat the process, substituting again your calculated x1, which is 4.3069, as x0 for your next iteration. So on the next iteration, we ended up with an x0 value of 4.3069. Substituting that to your function gives us this solution with a value of -0.0003. Substituting that to your first derivative gives us this solution with a value of 22.193. Thus, you end up with a solution for your x1 to be like this, with a value again of 4.3069. And at this point, our absolute error is now satisfied. Hence, we could now terminate the process. You could simplify the solution for your Newton's method by tabulating the result, much like the previous open method techniques. Thus, you end up with a tabulated solution like this, providing a column for your x0, your function x0, and your first derivative at x0, as well as your calculated x1. Here, I've taken a note by adding your absolute error and providing a column for your calculated error during each iteration, starting from the second iteration down to the last. The Newton-Raphson method. This method is also based on the Newton's method in approximating the root of your function. Hence, this technique still applies the tangent line in order to approximate your root value. However, a test for convergence is introduced in order to check whether the solution becomes convergent or divergent at a given particular initial value that you prefer. Just like your Newton's method, this technique is also applicable for both polynomial and transcendental functions. The process begins by assuming an initial value x0 that will be substituted later to the iteration. This initial value x0 is then subjected to convergence test in order to verify if the solution would be convergent or divergent. It follows that if the initial value x0 satisfies the convergent condition, then it is used for your iteration. Otherwise, a new initial value x0 is selected and then substituted to your convergence formula. The convergence formula, g of x, is actually equivalent to the absolute value of your function multiplied by its second derivative divided by the squared of this first derivative function, whereby we substitute your initial value x0 to these respective functions. If the value of your g of x, absolute value of your g of x, turns out to be less than 1, then the initial value selected x0 is convergent on a given particular root. Otherwise, this becomes divergent. If it is divergent, then you simply select a new initial value for x0 and then repeat the test. The iterative formula for your technique, Newton-Raphson method, is similarly based from your Newton's method. Hence, the iterative formula then eventually is like this. Let's try to evaluate and use this technique now, Newton-Raphson method, in evaluating our given function. Hence, we first establish a root of your function by equating it to 0 and then obtaining its first derivative, likewise its second derivative that will be used for your convergence test, and then assume any initial value as your corresponding integer initial value. In this case, the selected initial value is 5. Applying then the convergence test, using the initial value x0 equal to 5, we then substitute that to your respective function, giving us this solution with a value of 20. We then likewise substitute your x0 equal to 5 to your first derivative that gives us this solution with a value of 36, and substituting your x0 to your second derivative gives us this solution, leaving us with a value of 22. When we then solve for g of x, we then multiply your function fx0, which is a value of 20, to your second derivative function at x0, which is a value of 22, and then divide its product by the square of the first derivative at x0 with a value of 36, ending up with a calculated value now equal to 0.3395, showing us that this initial value x05 is convergent. We then start off the iterative process after verifying the convergence test and using the initial value x0, which in this case is 5. Substituting that to your function gives us a solution like this with a value of 20. Substituting that again to your first derivative gives us this solution, giving us a value of 36. We could then solve now for your root value x1 using your Newton's method formula, with this solution having a value of 4.4444. And then we repeat the process by substituting your calculated x1 to your previous value x0. Hence, the second iteration begins with an x0 value of 4.4444. Substituting that to your function gives us the solution with a value of 3.2225. Substituting that to your first derivative now gives us this solution with a value of 24.7029. And then calculating again for your new root value x1 gives us this solution with a value of 4.3139. At this point, the absolute error now would be computed to be like this with a value of 0.1305. Thus showing us that we need to repeat the process, substituting your calculated x1 to your previous value x0 again. Thus, on your third iteration, your x0 now is 4.3139. Substituting that to your function gives us this solution with a value of 0.1555. Substituting that to your first derivative gives us this solution with a value of 22.318. Thus giving us an x1 solution now equal to this with a value of 4.3069. Calculating for the error gives us an error of 0.0070, thus showing us that we need to repeat the process and then substitute x1 to x0 again. Hence, on the fourth iteration, your x0 now becomes 4.3069. Substituting that to your function gives us this solution with a function value of negative 0.0003. Substituting that to your first derivative gives us this solution with a value now of 22.193. And hence, we could now compute for x1 to have this solution with a value now again of 4.3069. Thus, if we compute for the error now satisfies your terminating condition, and then we terminate the process. Note that all calculated values seen on this iteration is rounded off to 4 decimal places in order to satisfy the terminating condition, which was established on the problem to be EA less than 0.00001, which involves 4 decimal places. Thus, summarizing then your solution, ending up with a tabulated solution now, much like your Newton's method, and it looks like this. Hence, you need to provide a column for x0, fx0, your first derivative at x0, and your calculated x1. In here, I again provided another column for your absolute error criteria, which eventually tells us when to terminate the process. This ends Module 1, Lesson 6.